This video segment is the prelude to the 3 segments that I'm planning to prepare, and they deal with modeling of honeycomb sandwiches, honeycomb sandwich structures in the Catia V5, and analyzing with its native FEA solver. I thought it was a good idea if I made this thing independent of doing any CATIA work, just to give you an idea of what we are trying to do and how many different ways are there to do that problem. Okay, so here is the situation. Uh, Finite element analysis of a simple sandwich structure with CATIA V5's native FEA solver. Okay, and I'm going to be uh, showing you 3 different methods of doing it. They're not necessarily the best or the only way. There may be other ones, but here is what I'm going to be doing. First of all, as far as the honeycomb is concerned, it's basically a very weak structure, uh, which is sandwiched between 2 skin 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 parts: top face, bottom face, and the core inside. Okay. Uh, this basically plays the role of an I-beam. In other words, in an I-beam, the flanges on the top and the bottom are meant to carry the bulk of the tensile and compressive loads, and uh, the web, which is right here, is intended to carry the shear load. Okay. Now here is an example, a real life example. I took it out of internet, and basically you have coffee cups here, paper coffee cups, which is placed between 2 plates, 2 very thin, cardboard plates, and glued together, okay, with an adhesive. And here is a guy standing right in the middle of it, and you can see that it can carry a lot of compressive load. Okay. Now, this is widely used because of its low weight. It's widely used in aerospace industry, among other places. And you can see that here is a cross section of a wing shown from the side, and the skin, outer skin and inner skin, is actually trapping a honeycomb structure in the middle. Okay, I think these are the references that I took it. Now, the specific problem that I'm going to be doing is a plate 254 millimeter by 254 millimeter square plate. And if you look at the true scale zoomed into this one of these corners, is basically the core is down here, the honeycomb is down here about 19 millimeter, and the top skin and the bottom skin, or top face and the bottom face, which basically holds this core together, bonded to the rest of the structure, is only less than a millimeter thick. Now, uh, we're going to model these type of problems 3 different ways. One is we model the top skin, bottom skin, and the core as laminated composite, and model it with shell elements. So that's going to be the first video in support of this present illustration. Okay, and so we are dealing with a single part, and that single part is just a plane, is a surface, and the surface is going to be basically carrying the information for all 3 components, namely top skin, bottom skin, and the core. Okay. Now, when I model, there's nothing fancy about this thing. It's just going to be a plane like that, or a plate like that, and I'm going to model it with quadratic elements, parabolic quad element, 10 by 10, as shown here. Okay. Then what you can do is you can model the top skin and the bottom skin as shell elements, in other words, the composite, laminated composite, and the core, you can model it as solid. So here is the top skin, bottom skin, and there is the core. You can see that it's modeled with solid elements. You can see that here. And just I've zoomed into this corner, notice that as far as the division of the top plate and the bottom plate, it's still 10 by 10, but there is also 10 layers, up to 10 layers of solid elements through this core. Okay. The third one is I will kind of do the same problem that I just showed you, except that it's going to be done as an assembly. It's going to be an assembly of three parts. So there's going to be the top face or top skin, which is going to be a part by itself. The bottom skin, just like that, another part, and honeycomb in the middle, which is a solid, solid part. Okay. Now, because we're solving this thing as an assembly, we have to put these things together, of course. We need to create analysis connection between them. In other words, how do these parts interact with each other? So, for example, one possibility is to assume that this top and the bottom are completely glued together, as in Katia is called fasten, or we allow sliding between the top and the bottom, which really doesn't happen in the case of honeycomb. So fasten is the more appropriate way, at least for the purpose that I have in mind. So this is the third approach, the third video segment in support of this present one, and it's going to be solving the same problem as an assembly. Notice that what I'm going to be doing is the top is going to be modeled with shell elements, and top and the bottom, and the middle one is going to be solid elements, similar to the one that I showed you earlier. Now, what you have to do is we have to make sure that when it comes to applying restraints, okay, these side faces of the solid, of course, they are clamped, and I have to make sure that the top edges of this top uh, top skin and the bottom skin are also clamped. Now, this applies to the second modeling approach and the third modeling approach. The first one is just shells, so you don't have that. Now, first of all, this problem, I got it from a video clip in support of Ever Barbero's finite element book, and he is doing the same problem with this data that I'm going to show you, and yeah, and but he's modeling only 1/4 of it. So this edge is clamped, that edge is clamped, and these are planes of symmetry, which can be done. However, I decided not to because uh, for different reasons. For example, if the top and the bottom faces were several layers of laminated composite at different angles, then of course the plane of symmetry may not exist. So I'm not going to be modeling the quarter, I'm going to be modeling the entire plane. Now, this is the table that is used in this video and in the book. A couple of things, notice that we have, first of all, units are here. This is the dimension 254, the height, the thickness of the core, and the face sheets, and the load that we're going to apply on top of the face sheet. Okay, but up here are the material properties. Units are in MPa, but let's watch a few things here. First of all, this is the face, the top face and the bottom face, top skin and bottom skin, and this is the core. A couple of things you notice that because the top face and the bottom face, we're going to be modeling with shell elements and think about a laminated composite, only one layer, of course. The only two, there's only four properties that I need really. Actually, there's five of them, and those are E1 and E2, E1 and E2. In other words, Young's modulus or modulus of elasticity in the direction of the fiber and perpendicular to the fiber. Okay, the Poisson ratio, and shear modulus in the 1-2 plane, in the plane of the composite. And for the other two, which in the case of classical laminate theory are not needed, but here, because we're using, CATIA uses and most software use the first order shear deformation theory, you also need these two values. But what I want to show you is that for the core, if you look at it, the the core is very weak uh, in the plane of the core. Okay, uh, this is about, I don't know, 1,000 times, 10,000 times small. So it's very weak. You can see that compared to what you see on the top face and the bottom face, these are pretty much zero. Now, ordinarily, you can put zeros here. The problem is that some software may be using the inverse of 1 over E1, and if they see a zero, basically they bomb out, okay? So Barbero suggests a small number like that. A Poisson ratio for the core is very close to zero in the 1-2 plane. And if you look at the shear modulus in 1-2, just like these were small, this is also very small. So basically, these are all zero. These two are zero. This is zero. But to avoid singularity, potential singularity software puts a small number. Now, the only things that are going to survive are these three. Now, these are shear moduli in the 1-3 plane, 3 being the direction normal to the honeycomb, okay? And you can see that. And then there is a shear, there is a normal modulus to the honeycomb, which is substantially bigger than E1 and E2 for the face, 10 times bigger, and he's advocating that. Now, uh, this is responsible for carrying all the, this and G1 and G13 and G23 are responsible for carrying all the compression load that you may put on the sandwich structure, okay? The pressure is given here, okay? Yeah, so I again, I want to emphasize that when you compare the face and the core is very weak compared to the face in terms of modulus in the 1-2 direction, and the same thing with the shear. The shear, you can see the same thing with these two. Now, this does not apply to uh, this does not apply to the face, because the face is a shell. It's assumed to be incompressible, but the core is has this number. What I really wanted this green rectangle to be over there. Doesn't matter. Now, when it comes to modeling it in CATIA, obviously you have to input the material properties. First of all, I want to remind you, this is a orthotropic material 2D. This is going to be used for the top skin and the bottom skin, same property. And these are the numbers that you see in the previous table I put it here. Down below here are the strength properties that we're not looking at it. We're just looking at the stresses. Okay, we're not looking at whether they fail or not. And density, we don't need it because we're not really doing a dynamic problem. Now, the tab which is composite, uh, first of all, these things, although they're there and you can check it for management purposes, bill of material purposes, but for FEA purposes, it doesn't matter which one you do. All you need to do is to put the correct acute thickness, which means the thickness of the top skin and the bottom skin, which was 0.711 millimeter. This is all we need. Okay. Now the core can be modeled as a honeycomb, and when you look at that, you really need three numbers: normal modulus, which was that big number 10 times of what we had in the case of the face, okay, and the shear modulus in the XZ and YZ plane, namely 1-3 and 2-3 planes, okay. And once again, these are irrelevant. The thickness, however, the thickness of the honeycomb, we have to input it as the whatever the thickness we've got. In other words, 19.05. Now, another option is to create the core as declare it as basically orthotropic 3D material, but the only the only three things that are going to be used here really are shear modulus in the X and YZ plane, and the normal or is that the normal these are the that we want, and the normal Young's modulus. So this data that you see here, I took it from that same table, except that we're not going to do it like that. And by the way, look at the thickness of the honeycomb, which is 19.05. Okay. Now there is an excellent resource for honeycomb uh, for honeycomb data. These data that you saw in the table I'm using, really they either come from a supplier or from testing yourself. There are some simple calculations that you can do, which are non-trivial, by the way, where actually it estimates the properties, these E1, E2, E3 of a honeycomb based on the constituent material. Okay, a good reference for that is a textbook by Gibson uh, and Ashby. It's very good, the theoretical development. But generally speaking, here's a supplier, you go to their site to see what they sell, and then you get the data sheet. This is a typical data sheet from them, and you look at it. This is aluminum honeycomb. But notice that the only thing that you use is one modulus and two shear moduli. Moduli, shear, and normal. That's all you need. Okay. So I'm going to stop this thing. So we go back and do the three tutorials that I promised you. The first one is using primarily shell elements. The second one using shell and solid elements as a single part. And the third one is a shell solid as an assembly of parts. Okay. All right, folks. Good luck.